Hi, this is Maggie. In this video, we're going to solve a problem that will be easier to solve if we have a way to dynamically allocate memory. Before we get started, I'm going to quickly give you some tips for how to get the most out of this video. First, if you have problem solving with Python, read up through Chapter 6. If you don't have it, you can still learn a lot from this video. Open up idle and follow along with Python as I work. Sometimes I'm going to suggest you pause the video and complete some steps on your own. When I do that, pause the video and do your best to complete the steps on your own. The way to learn to program is by programming. You can watch and learn if you work along with me. Remember, you can always pause the video and try something or go back and watch again. You don't have to wait for me to tell you to pause. There are some automated exercises in the description of this video. The exercises work with the same code or similar code to the code in the videos. After you've completed the video, try the exercises to cement the concepts in your mind. Now let's get started. We're going to solve a problem for a friend who likes data and healthy living and wants a way to track their weight. Specifically, your friend would like a program that computes a weighted moving average of their weight and graphs the weighted moving average against the weight measurements for the latest 2-week span of data. After discussing the problem with your friend to gain a deeper understanding, you suggested they could use spreadsheet software to do this, but for several reasons your friend would prefer that you program it for them. We will skip over the first step of the problem-solving process in this video and begin at the point at which the problem is well defined in order to keep the video shorter and focus on designing solutions that use lists. If you don't want to skip this step, pause the video and think about the questions you would ask your friend based on what you know so far. Your friend has a feature-rich solution in mind, but you've narrowed it down to something much simpler as a starting point. The program will function as follows. It will open a file of weight data with one weight measurement per line. You can assume the weight measurements were taken at roughly 24-hour intervals, for example, at 6 a.m. each day. The program will prompt the user for a new day's weight. It will then display a graph showing the weights over the last 14 days and the weighted moving average for each of those days. Once finished displaying the graph, it will write the weights back to the file. The weighted moving average will be computed as the sum of the weight 5 days prior times 1, the weight 4 days prior times 2, the weight 3 days prior times 3, the weight 2 days prior times 4, and the current weight times 5, divided by the number of weights, 15. The smoothing function makes the weight trend over time clearer. For example, suppose the last 14 weights are 150, 152, 151, 152.5, 153.5, 152, 155, 154.5, 156.5, 152, 155, 156, 157, 156.5. A graph showing these weights is noisy, with a lot of ups and downs, but the smoothed graph shows a very clear trend upward, with just one dip. An example of the calculation for a smoothed weight for the 5th day would be the first day's weight, 150, plus the second day's weight, 152 times 2, plus the third day's weight, 151 times 3, plus the fourth day's weight, 152.5 times 4, plus the fifth day's weight, 153.5 times 5, divided by 15. Thus, we are including the weight 5 days prior, but with much less weight in the calculation, than the current day's weight, which has a little more weight than the weight from the day prior, etc. For the first 4 days of data, the smoothing function should use the current weight times 5 divided by 5 for the first weight, the current weight times 5 and the prior weight times 4 divided by 9 for the second day's smoothed weight, the current weight times 5 plus the prior weight times 4 plus the weight 2 days prior times 3 divided by 12 for the third day's smoothed weight, etc. So we will be using the same formula, but only for as many days as we have. This will also work if there aren't at least 5 values in the file. Pause the video and take a moment to think about this problem. Our next step is to identify and select among solutions. Because this video is about solving a problem with lists, think about how you could use a list or lists to solve this problem. Pause now. How did you do? Did you think that maybe we could read the values from the file into a list?
A list is a natural way to store sequential data. We use the same algorithms to process list data as we use to process data that we read from the console or read from a file, one element at a time. But lists also have some built-in methods and functions that can make processing them a little easier. For example, we can sum an entire list using the sum function. We can search for specific values within a list, and we can slice lists into smaller lists. We might also store the smoothed values in a list. Imagine that we could write a generic plotting function that takes a list as a parameter. We could pass in the list of raw weights, and we could pass in the list of smoothed weights, but write the function only once. If you hadn't thought about storing the weights and the smoothed weights in lists, pause the video again and think about the way we would structure a program to read weights from a file, obtain a new weight, smooth the weights, and plot both raw and smoothed weights with the weights stored in a list. Pause now. I think what's going to be most interesting and challenging in solving this problem is the algorithms we use to work with the data. It's really helpful to draw a list when working with one. To draw a list, draw a long, thin rectangle broken into boxes with vertical lines. Put the indices of the elements over the boxes, and put the elements inside the boxes. So, for example, for the weights we had before, which can be our working set, there are 14 weights. We put one in each box. The indices will run from 0 to the number of weights minus 1, or from 0 to 13. We draw these above the boxes. When planning our algorithms, it is sometimes helpful to use arrows to point to elements we're referencing. These arrows will correspond to index variables in our program. For example, if we plan to iterate over the list and find the lowest weight, we might draw an arrow pointing to the element at index 0. We will move this stepper arrow along the structure as we consider each element in the list. We will also want an arrow pointing to the smallest weight we have found so far. That will be a most wanted holder index. It will always point to the smallest weight that we have found as we consider each element one at a time. You might recognize these variable roles from the repetition structures chapter. The algorithms that we use to process a list are looping algorithms, and we will use the same structures and variables. Pause the video and use two arrows to find the largest weight in the list. Begin with the most wanted holder arrow pointing to element 0, and the arrow that will hold the value we're currently considering, the stepper arrow, pointing to element 1. Compare the two values, and if the value at element 1 is larger, move the most wanted holder arrow to point there. Then move your stepper arrow to element 2, etc., until you've considered every element in the list. Pause now. How did you do? If we're going to do this, we start by having our most wanted holder arrow pointing to element 0 and our stepper arrow pointing to element 1, and we're looking for the largest value. So we compare 152 to 150, and it is larger, so we move the most wanted holder arrow to point to 152. We are done considering, so we move the stepper arrow to point to the element at index 2. Compare. 151 is not greater than 152, so leave the most wanted arrow where it is, and move the stepper to index 3. 152.5 is greater than the value pointed to by our most wanted holder arrow, so move that to point to 152.5, the value at index 3. We're done considering that element, so move the stepper to index 4. Compare. 153.5 is greater than 152.5, so move the most wanted holder to index 4. We're done considering, move the stepper arrow to index 5. Compare. 152 is not greater than 153.5, so leave the most wanted holder arrow where it is, and because we're done considering, move the stepper arrow to index 6. And you would continue in that way to find the largest value in the list. That's how an algorithm that looks for a best fit value in a list can be planned or checked using a drawing of a list. Of course, you can also use a desk checking table. Now, the interesting algorithm that we need to work out is creating the list of smoothed values, the weighted moving average, from the list of raw weights. The algorithm is further complicated because we don't know how many weights we'll have. At a minimum, we'll have 1 because we'll be obtaining one weight after we read the values from the file. We'll have 1 if the file is empty. And we really only need to create the smoothed result for the last 14 values in the list. So that's a decision we need to make. Should we smooth the entire list in case we will want to work with those values in the future? Or should we smooth only the last 14, or fewer if there aren't 14 values in the file? Let's look at how we'll smooth an individual value, and then when we make decisions about the structure of the program, we'll decide if we're going to smooth all of the values or only the ones we need to plot. Again, if we use our image as an aid, let's start by looking at the last value. If we are interested in smoothing the value at index 13, we're going to multiply that value by 5, and sum that with the value at index 12 multiplied by 4, the value at index 11 multiplied by 3, the value at index 10 multiplied by 2, and the value at index 9. We'll then divide the total by 15, which gives us roughly 156, and store the result in our list of smoothed values. Now let's look at the value at index 12. To smooth that, we multiply the value by 5 and sum that with the value at index 11 multiplied by 4, the value at index 10 multiplied by 3, the value at index 9 multiplied by 2, and the value at index 8. We'll then divide the total by 15, again, giving us approximately 155.6, and store the result in our list of smoothed values at index 12. The trick here is finding the pattern, so we can easily write a loop to smooth each value. We could then consider the special cases of the values that are closer than 4 indices from the first value in the list. Pause the video and come up with an algorithm, Python or pseudocode, to smooth each value in a list. Pause now. How'd you do? Sometimes it's helpful to write values out in a column to look for patterns, as they would appear in a desk checking table if they were variables changing over time. I might notice that I take the value that I'm smoothing, and I multiply that by 5. Then I take the value at 1 less, so I'll call that I minus 1, and I multiply that by 4. Then I take the value 2 less, I'll call that I minus 2, and I multiply that by 3. At I minus 3, I multiply by 2, and at I minus 4, I don't multiply, or I multiply by 1. And so I see this pattern where the index is descending by 1 each time, and the number I multiply by is also descending by 1 each time. The index is descending by 1 starting at I, and the number I multiply by is descending by 1 starting at 5. So, given I could have a loop running from 0 to 4, and let's use j to control that loop. To get the index of the value I'm considering, I could subtract j from I, and to get the value I'm multiplying by, I could subtract j from 5. I end up with the value at index I minus j times 5 minus j. When you are developing a solution to a problem, it's okay to make sure bits of your algorithm work properly. I'm going to write a very short program in which I hardcode my list to include the values that we're working with, and I'll write just this algorithm to smooth and create a new list and print it. And I can check my work against calculations I've already done in a spreadsheet. So to do this, I'll open a Python script window and annotate a variable weights of type list float. And I'll just put in a comma-delimited list of weights. I'm going to pause and do that and return. Now that I have my list of weights, I will annotate my 2 steppers, I and j, as integers. I'm also going to need the list of smoothed values, which I'll call averages. Annotated as a list, and I'll set that equal to the empty list. And I'll write my loop to add the averages into the list of averages. Now we haven't discussed whether we're doing the entire list or just the last 14 values. We haven't discussed how we'll compute the first 4 values as a special case. So I'll just skip the first 4 values for now and do the rest of my list. So I'm going to write for I in range len weights colon. And let's talk about that for a moment. If I want a stepper variable to iterate over the indices of a list, this is the way I do it. Len weights is the number of values in the list, in this case 14. And so range len weights will be a range from 0 up to, but not including 14, in increments of 1. In other words, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Each time through the for loop, I will take on the next value in this range, which will make it a stepper I can use to iterate over the list. Now for now, I'm going to write if I is less than 4, colon, averages.append 0. That will put zeros in the first 4 spaces in the averages list, since we haven't talked about how to calculate them as a special case. Now when else colon for the case where we can use our formula to compute the weighted moving average, or smoothed value. I'm going to sum the weighted values, so I'll need to annotate a variable called total of type int, back where I annotated my other variables. But now, inside the loop, I'm going to assign 0 to total. So imagine we've just reached the element at index 4. We want to start with a total of 0, which is an accumulator, and we want to loop over elements 4, 3, 2, 1, and 0, multiply them by 5, 4, 3, 2, and 1, respectively, and accumulate them into our total. And then the next time through this loop will be at index 5, and we'll want to reset total to 0 again and do our sum again. So that's why we set total equal to 0 right here. Now we'll write our inner loop, which is going to consider the current and prior 4 values in the list. We'll write for j in range 5, total plus equal, weights sub I minus j times 5 minus j. That's our formula. The first time through this inner loop, j is 0 and I is 4. So we're taking the value at index 4 minus 0, or 4, and multiplying it by 5 minus 0, or 5, and adding that to our total. Then the next time through the loop, we're taking the value at index 4 minus 1, or 3, and multiplying it by 5 minus 1, or 4, and on until we reach the value at index 4 minus 4, and multiply it by 5 minus 4. Once we have that total, we can append the total divided by 15 into our averages list by writing averages.append total divided by 15. Now, if we print averages at the end of our outer loop and run the program, it prints the list, and if we compare those values to the values calculated in the spreadsheet, we can see that our algorithm works for this general case. Our smooth values are 152.3 at index 4, 152.36 repeating at index 5, 153.3, 153.86 repeating, 154.86 repeating, 154.1, 154.43 repeating, 154.9, 155.63 repeating, and finally 156.03 repeating. This is a general case because I'm not handling any special situations. I'm not handling the first 4 elements in the list, which is also not handling the case if there are fewer than 5 elements in the list. Pause the video and take a moment to review this algorithm we have just written and compare to the calculations by hand and confirm that it works and makes sense. Then think about how we should handle the special cases of the first 4 elements in the list and lists smaller than 5 elements. Remember that for the special cases, we'll weight as many elements as we have available in the same way, but we'll divide by however many values we have. So for example, if we have only 1 value, we multiply by 5 and divide by 5. If we have 2 values, we multiply the first by 5 and the second by 4 and divide by 9. 3 values, we multiply the first by 5, the second by 4, the third by 3, and divide by 12, etc. Pause now. How'd you do? Maybe you came up with a solution that's better than mine. My decision was to change our inner for loop to a while loop that will either exit at j equal to 5 or exit if I minus j is less than 0. This way we never try to index into a part of the list that doesn't exist. But what about the part of the solution where we actually take the average? We divide by 15. What value should we divide by? One solution to this is to count the number of values we're totaling. So we could create a new total, maybe called num values, and add 5 minus j to it each time through the loop. If we drop out of the loop before 5 iterations because we're near the beginning of the list, we will have added only the values that we added into the total. But I thought that maybe I could find a pattern that would let me solve the problem without an accumulator. There's a formula for summing the numbers from 1 to n, sometimes called Gauss's formula, which is n times n plus 1 divided by 2. So the sum of the numbers from 1 to 5, as we know, is 15, and that is 5 times 6 divided by 2. The story is that Gauss's teacher wanted to occupy his students, so he set them the problem of summing the values from 1 to 100, and Gauss noticed that the problem was really a bunch of totals of 101, 100 plus 1, 99 plus 2, 98 plus 3, etc., and came up with the formula. I have no idea if that's true, probably not, but it's a fun story. I can use Gauss's formula and the value of j when we exit the loop to help me. If I make a table, I see that when j is 5, I have made it through the full 5 iterations, and I want to divide by 15. When j is 4, I've added 5 plus 4 plus 3 plus 2, or 14. When j is 3, I've added 5 plus 4 plus 3, or 12. When j is 2, my sum is 9, and when j is 1, my sum is 5. I can get the total I want by subtracting j from 5 and plugging it into Gauss's formula, then subtracting that from 15. So for example, when j is 5, I've made it through all 5 iterations. I subtract 5 from 5 and I get 0, so I subtract nothing from 15. When j is 4, I subtract 5 minus 4 and get 1. 1 times 1 plus 1 divided by 2 is 1, and when I subtract that from 15, I get 14. When j is 3, I subtract 5 minus 3 and get 2. 2 times 3 divided by 2 is 3, and when I subtract that from 15, I get 12. Similarly, I get 9 and 5 for the last two values. So to make our program work regardless of whether we're at the beginning of the list or further in, we can write an inner while loop with the header while j less than 5 and I minus j greater than or equal to 0. Total as usual, and make sure we have an initializer and an updater for j now that we're using a while loop and not a for loop. And then after the loop, rather than dividing by 15, we'll divide by 15 minus 5 minus j times 6 minus j divided by 2. Or with algebra, we can simplify that to 11j minus j squared divided by 2. Running the program, and comparing to our spreadsheet shows that this works. Now you might consider that it's easier to read to simply count the weights within the loop rather than using that odd-looking expression to calculate the number of values, and you are definitely correct, especially for a beginner programmer. I like the mathematical solution, but when I use it in my program, I'm going to put a comment over it describing where it came from. As a general rule, I will defer to a calculation that exploits a pattern in the data rather than using a variable or logic. So now we've worked through the most interesting and the most difficult algorithm in our program, the smoothing or weighted moving average algorithm. If we rerun the program with an empty list and with a list of just one element, the algorithm works correctly and does not crash. At this point, let's put together a functional decomposition solution for the entire program. The focus in this video is on a solution that uses lists, so I will not go through programming this solution except where it involves the list. But first, Pause the video and see if you can come up with a functional decomposition that will solve this problem. Remember the specification. The program will open a file of weight data with one weight measurement per line. The program will prompt the user for a new day's weight. It will then display a graph showing the weights over the last 14 days and the weighted moving average for each of those days. It will then write the values back to the file. Pause now. Welcome back. Did you come up with a functional decomposition for this problem? There is no one right answer to this, but you can compare your solution with mine. I decided to have 4 functions besides main. One called read weights, which will read the weights from the file and return the list of weights. It will take the file name as a parameter. The second is called smooth, and it will take the list of weights and return a smoothed list of weights. The third is plot. It will take a list of weights and a color and plot the weights in that color. The fourth is write weights. This will take the list of weights and the file name and write the weights to the file. Given the code that we've written in either my functional decomposition or yours, pause the video and see how much of this you can program. I have some suggestions for how to develop this incrementally. Just put the keyword pass in write weights. There's no reason to worry about that yet. And you can make read weights a stub that just hard-codes the same list of weights we've worked with and returns it. We have the code written for smooth. That leaves you with trying to figure out the plotting. You will write one plot function and pass each list to it. Remember that you are only plotting the last 14 values in each list. Pass different colors with the lists so the lines are distinct. You can use turtle graphics for your plots. If you get ambitious, write the file reading and file writing code. Pause now. How'd you do? I'm going to share my program. Let's go through the plot function. The plot function is passed a list of values to plot and a color. We are plotting only the last 14 values in the list, so I am passing in only those 14 values. When I plotted the values in our lists, they were so close that they obscured each other on the plot. To scale them a bit, I subtracted the mean average from each value and multiplied by 10. This has a sort of zooming in effect so that the differences are magnified. Here's what it looks like running. And as compared with the graphs produced in spreadsheet software. It looks pretty close. Within the function, I annotate a mean variable and calculate it by using 2 handy functions, sum, which will sum all values in a list, and len, which gives me the length of the list. I raise the turtle, set the color, and then move the turtle to the location of our first dot. To center the plot roughly in the window, I start plotting at -150 and put each dot an x interval of 25 pixels to the right of the last. For the y-coordinate, I subtract the mean from the value and multiply by 10. I set the turtle's position for the 0th element in the list and then put the pen down, loop over the remaining values, and plot a dot at the turtle's current location, and then move to the next location. I use I to calculate the x-coordinate, and use I to index into the array of values. I started by just plotting each dot, starting at 0, each 25 pixels to the right, and then I slowly adjusted it to look better. This was my result. In the next iteration of this project, I would add axes to the plot. Let's look at where I invoke this from main. In main, after I calculate the smoothed values, I send the last 14 of the raw values to the function plot, and then I send the last 14 of the smoothed values to the function plot. Is this going to be a problem, though, if there aren't 14 values? What I'm doing here is taking a slice using square brackets and a colon. And remember, if I omit the last value, that refers to the end of the list. Instead of figuring out how far the 14th value is from the start of the list, I'm using negative indexing. So weights sub -14 colon close bracket. But I could take the length of the list and subtract 14. That's what negative indexing does. But here's the cool thing. If there aren't 14 values in the list, it just uses the start of the list as that index. This will work even if the list is empty. Let's look at read weights, and then perhaps you can try write weights if you haven't already written it. The read weights function is going to return a list containing the data read from the file. We invoke it down in main as weights equals read weights, and then we pass in the file name as a parameter. We're assigning the result to a list variable, weights. In the function read weights, we define a list called weights. We annotate that as of type list float, and we can annotate that way because I've imported list from typing. I've also imported text.io from typing to annotate my file reference variable. So that's at the top. From typing, import list, text.io. I annotate the weight file reference variable as type text.io, and I assign to it the result of open, and I pass in the file name as parameter. Read mode is the default, so I don't have to pass in a mode. I then read the first weight from the file, and while it is not the end of file, I append it to the list of weights and read the next weight from the file. When I append, I cast the weight that I read to a float. If I were to look at that value before casting, it would look like a string with the new line as part of the string. If I used read lines instead of reading one line at a time, I would get a list of strings with new lines appended, and I would have to go through that list and cast each element to a float and reassign it to the list. So there are at least two ways to do this, but both ways I have to cast each element to a float. I choose to do it one element at a time. Once I'm done reading the last weight, once I've reached the end of the file, I close the file and return the weights list. Now, see if you can write the writeWeights function. It takes the list of weights as a parameter and the file name, and it returns nothing. Pause now. How'd you do? So again, we're going to annotate a file reference variable as text.io, and we're going to open the file. But this time we'll pass in both the file name and a string W for write mode. And then we will iterate through the list and write each element to the file. To do this, I must reverse what I did when I read in, cast a float to a string, and append the new line. That way each element will be on its own line. I then close the file. Now I could append the last value of the list to the file by opening the file in append mode and writing just the one value. To do this, I would have to know if the file ended in a new line or a value. This is a fine solution and involves less disk I/O. Just make sure you store that information of what the last value in the file is so that you don't accidentally write either two new lines, so you have a blank line, or two weight values onto the same line. Finally, just looking at main, after I read the weights from the file, I obtain a new weight from the user using an input statement and append it to the list. After that, I smooth and plot, then write the weights to the file. And that is this problem solved. We worked a lot with lists, writing a list to a file and reading from a file into a list, slicing a list, iterating over lists for several algorithms, and writing the somewhat complicated smoothing function, which moved over one list, looking at an element and its 4 predecessors, and using a formula to append a calculated element to a new list. You now have written a complete program with lists. I recommend that you close your script window, open a new one, and rewrite the program yourself from scratch. Check back with the video or the program you wrote earlier, only if you get into trouble you can't get out of. Once you've completed that, you're ready to move on to solving your own programming problems using lists.